And every time I see computer science students, I was delighted because I can trust them with my software engineering project. But I have to send them for one course first. Otherwise, half the job in my lab they cannot do. Because they have no idea what is frequency. Understand? They have no idea what is frequency. It's not, computer science syllabus doesn't include anything that will teach you to see things in terms of frequency domain. Frequency as in how many hertz, that sort of thing. Right? And you listen to music processing. You listen to speech processing, for example. All these need to be done in the frequency domain. And speech processing, music processing, it's also something that computer science people are doing, right? So how can you not know the fundamentals? So when I joined NUS, I told associate management that we need to introduce some sort of a course, right? It need not be the full-fledged signal processing course as done in engineering department, because there are certain things there that you will need to know. But there are certain things that if you know, it will actually strengthen you. When you join, say, a research lab doing speech processing, doing image processing, right? You need this kind of knowledge that I'm going to teach you. Alright? So although this is not a core CS course, I think it's a very useful elective for you if you want to venture into music, in speech, in image processing. Alright, because there are techniques here that you need to learn in order to function well, so that you don't lose out to people from engineering side. Alright? So that is the motivation. Alright? Okay? So, any questions so far? I like the lectures and tutorials to be very interactive. So stop me at any point in time if you have any questions, alright? And there's no point for me to carry on the lecture if you don't understand. Okay? And I like to look at your face, because by looking at your face, I have a sense of whether you understand or you don't understand. That is also one of the major reasons I don't want to record and I don't want to webcast. Because the moment I record or webcast, 60% of what you here will be gone, I think. Right? That is the experience from other professors here, right? And then you get, you don't know who you are teaching actually. You don't know whether the students understand. Okay? So even if you are too shy to put up a hand to say you don't understand, when I say whether you understand or not, if you just turn your head like that, at least it gives me a signal that I need to rephrase my explanation, understand? Alright? And if you understand, just nod so that I know I can spend more time on those things that I need to spend more time on. Alright? Okay? So, this calls Introduction to Media Computing. So the first question that comes into your mind is, what exactly is media, right? But before that, I haven't introduced myself. Right, my name is Kim, right? My surname is Ng, Ng. Ng is pronounced as Ng, right? And I think local people know about it, but a lot of foreigners will pronounce it in a very funny way, N or Ng or whatever, right? It's Ng. Okay, so Ng is my surname. You can call me various ways. You can call, some people like to call me Prof. Ng, some people like to call me Dr. Ng, some people like to call me Ted Kim, my first name. Some people like to call me TK, right? If you call me TK, that's absolutely fine. That's how I find my email also. Okay? And my office is in Tom 3, the new building, 0208. Alright? Now when the course stabilizes, then I will work out something with you. We'll see how things go, right? For how to help you to clarify some of the things that you don't understand. Okay, we have two teaching assistants, right? They are students who have taken this course before. Yao Yi has taken this course 2 years ago. She's now working on the FYP with me. Ivan took the course last year, right? And they are good students, they are very good students. They will take you for the tutorial classes, right? Now, they will also be the one grading your tutorial classes, your tutorial assignments, right? Now, I will be doing the lecture, and I will find time to see, as I say, I'll be talking to how to help you in addition to the lecture and tutorial hours. Alright? And all of you are on Canvas now, right? You have downloaded this set of slides from Canvas, right? And in Canvas, there's a forum discussion, right? As far as possible, please use that forum to do discussions because number one, usually it's like FAQ. A lot of people have the same question. Number two, as much whatever questions you ask and we answer, we want to share it with the entire class, right? So that everyone can learn together. Okay? So please ask many questions. So the lecture is 10 to 12, and I apologize again for being late. Right, you'll not have it again. It's at this place, LT15, plus tutorial classes. Tutorial classes, that's Thursday, that's Friday, 2 sessions. Right, so you need to bid for your tutorial class. You just need to attend one of the sessions. Okay. The final exam is in person, not online. Final exam, by the way, is open book, meaning you can bring all kinds of materials with you, but not electronic materials. You cannot bring a computer or your cell phone with you for the exam, right? You cannot go on internet, for example. You can bring any printed materials with you, the lecture notes, tutorials, and any books from library from anywhere. Okay, it's unlimited. You can just bring all the reference materials with you in open book. So there's no need for you to memorize anything. So what I want from you is to understand fully, right? Because the exam is not designed for you to do tedious calculations or math manipulation, not like that. This is not a mathematics course. The questions are designed to test your understanding. Okay? To test your understanding, if the concept is right, you find the exam very easy. Okay? And the final exam will be on the 7th of May. In the morning, 9 to 11. Alright. Assessment. Now, tutorial assignments, there will be a series of tutorial assignments. Tutorials are actually meant to help you understand the material. Okay? Now, try to do, no, in fact, you have to do everything by yourself, right? You try to understand. Okay? Tutorial, 20% only. There will be a course project, and it's likely to be individual projects. Right? So you have to work on the course project by yourself, and that carries 30%. Okay? The course project, I release it somewhere a few weeks later. Right? So you see the course structure now, right? The tutorials, no point cheating yourself by copying or whatever, no point, because if you don't understand the tutorial, don't understand the material, you're going to have problems with your project, you're going to have a lot of problems with your final exam. Okay? And project, as I said, is most likely individual project. Final exam, open book, right, 50%. Okay? There's no midterm for this course. There's no midterm exam for this course. Okay? But I may introduce some quizzes. This one, I'll see how the class performs, and then I may introduce some. Okay, so this assessment structure is subject to some minor modifications. Okay, but by and large, it is something like that. Okay, now some examples of mathematics that we go through just to let you know what kind of equations you'll be seeing. Right, you'll be seeing. You must be familiar. You must be okay with integration sign. You know the limits of integration, the summation, and the limits of the summation. Okay, and you must. All of you know what is the sine wave and the cosine wave, right? Right. In fact, you may see complicated equations like that. But all that I need from you in this course is to know what is a sine wave and what is a cosine wave. And have you heard of integration by trapezoidal rule? Have you heard of that? When you do integration, numerical integration, by counting the area under the curve. Right? You just need to do that, okay? As I said, this course, I'm not testing your math. I'm capitalizing on the fact that most of you, if not all of you, are computer science students. You like to code, and so even for integration, let's do the coding way and numerical way. Okay? So, and then there's one more thing that some of you may not have come across. I'm not sure. Can I assume that everyone knows what is a complex number? Has anyone not come across a complex number before? A complex number, real part and imaginary part. We'll be using complex numbers. Okay? And when you attend classes in mathematics, complex number, the imaginary number is denoted as I, right? When you go to engineering and computer science, the I is replaced by J, understand? Okay? Because I in engineering is a reserved word for current, electric current. Okay? So everyone uses J. Okay, and J, and in fact I like to use J because all J is less likely to be mistaken as 1. Right? I looks like a 1 if you use the top point off. Okay? So you'll be doing this. And then there's something called Euler's formula. Who has not come across Euler formula here? This formula. It's okay if you don't know. All have come across it, very good. Oh, okay. Right, it's okay if you don't know. Just this one, just take it this way. Okay, just take it this way. We are not going to dig further why this is equal to cos plus j sine. Right? Now, so you'll be dealing with equations like that, and you'll be doing something called omega. Omega is equal to 2 pi f. You study physics, right? Right? You study physics, right? Frequency, let's say if you go 1 round, if you go 5 rounds per second, what is the frequency? 5 hertz, right? 5 cycles per second, right? 5 hertz, right? But every round is 2 pi, right? Right? So 2 pi times f is how many radians per second, right? So that's the angular frequency. So sometimes instead of 2 pi f, we will write it as omega here. Okay? So this will be some of the things that you need to be familiar with. And and there will be something called delta function, right? Delta function, which I'll explain later. Okay, and there's something called convolution. How many of you have done deep learning or have heard of deep learning before? How many of you have heard of convolution neural network, CNN? For those of you who have done CNN, convolution neural network, I'll request that you go to the toilet and flush your knowledge, understand? Okay? Because the convolution neural network, the convolution used there, they make use of the gist of convolution, but they did it in a slightly different way. Okay? There is something called stride, right? you can jump your whatever. In real convolution, no such thing. Okay? So we'll be doing the convolution the classical way. Okay? And that's the only convolution we do. Right? Okay? So the neural net, the deep learning type of convolution, the CNN, made use of this concept. Okay? But they use the gist of this concept, but they, for efficiency, they implement it slightly differently. Okay? And you know something, we will be learning what is an impulse. Right? Impulse. And impulse is quite literally an impulse, right? It's a big punch, like impulse. So what are media? Right? Media in fact is the lead to grow over time, right? Basically, in broadly speaking, we can classify media into audio, right? Images, video, text, right? Okay. Then to this group, in fact, there are subclasses, right? You can go into say graph, whatever that sort of thing. Okay. Now, in handling many of these type of data, you do need different types of knowledge. Okay. Now, one of the things that, as I mentioned, one of the things that you ought to know, if you want to go into audio processing, right? You must know something about frequency, right? When I ask you to, okay, that's the generation gap between you and me. My generation, we grew up watching movies like The Sound of Music. Have you heard of the movie The Sound of Music? Right? And then there's a song called Do Re Mi, right? Right? Do a dear, a female dear, right? So when we say Do Re Mi, we are talking about the pitch, right? The musical pitch, right? That's the notion of frequency, right? That's the notion of frequency, okay? So, in this course, the biggest difficulty that you encounter is you need to have a change of, you need to be able to think in a different domain. Okay? So there is something called the spatial domain, which is like the x-axis is the time domain, right? The waveform, the reason we hear something is because of vibration in the air, right? And the speed of vibration and the strength of the vibration changes over time, right? So you can plot over time, right? That's in time. Now, if you let's say if I say do, right, one pitch, do, you can see that it's like some waveform, right? There's a consistent waveform throughout the time, right? But you can represent this interval of waveform by just one number, which is do, right? Right, at the time. Right? Meaning a time domain signal can be represented in the frequency domain by just one instant, right? If the axis is the frequency, right? It's so frequency, right? Right? Let's say 400 Hz, for example. Okay? So you need to switch between the two domains. And most of the time, it will be easier or more convenient to work in one domain and not the other. Okay? And in the era of deep learning, neural network, it is still very useful because certain type of input is better to be in certain domain, then you save a lot of time for your network to run. For example, if you are talking about just recognizing the re mi, right? Instead of feeding the waveform like that into your neural network, right? If you can compute that it is actually a do followed by re, and you feed that into a network, you save a lot in images, you see CNN was developed by the scientist that eventually won the Turing Prize 3 years ago, right? CNN was done on images, on handwritten characters, right? And there is no notion of frequency over there, right? Although it uses convolution and things like that. But what I'm going to say is, a lot of things that we do in audio, the techniques that we learn in audio, can be applied to images also. And the reason is very simple. They are both signals. Audio is a one-dimensional signal. The axis is time, right? The vibration over time. Vibration in air over time. In images, we call it spatial, right? X-axis and Y-axis. And the grayscale or the color changes with space, right? So there's also a notion of frequency in images, and I'll teach you how to see that. And of course, it's a video, right? Video is three-dimensional, you have another time dimension, but not just images. And of course, we have text, and in this era, you can't run away from text, right? There is a university policy on ChatGPT. We have to learn to live with ChatGPT, right? Okay, so I encourage. So last year in the course project, I included a 5 marks at the end of course project. I say use ChatGPT to give me a pleasant surprise. With respect to this, regarding the course this project, and some of them did give me some pleasant surprises. Okay, ChatGPT. So what I'm trying to say is, we should learn to use ChatGPT, but you have to be careful. If you can only live with ChatGPT, if you cannot live without ChatGPT, then it is a problem, right? Meaning, you have to learn the fundamentals. Okay, ChatGPT should be just a tool to enhance yourself. You cannot just rely on everything on ChatGPT, right? Okay, and when to use ChatGPT and things like that, I elaborate that when the assignment comes, right? Essentially, the concept is you can do whatever you want, but acknowledge it, right? If you use ChatGPT for this part of the answer, tell me, okay? Tell me, otherwise it is cheating, right? Okay? And number 2 is you have to be responsible for what you submit using ChatGPT, right? Okay, if ChatGPT gives you something stupid and then you say it's not your fault because it's ChatGPT, I cannot accept that. Whatever you submit, you have to be responsible for it. Okay? Now, in fact, that's the same for your assignment, your projects, or whatever. You're free to reference anything in open source on the internet, but you have to quote and acknowledge the source. Right? If you don't acknowledge the source, you treat it as plagiarism, and plagiarism is very serious here. Okay, you copy from here or copy from each other, it's very serious. For this course itself, I have failed students, a few students already, because they copy from each other for the assignment, right? So don't do that. As I say, the final exam is 50%, so you copy now, you're just cheating yourself. Okay? Now, signal processing, the various topics that we'll be going through will be, we are actually going to do something called Fourier series and Fourier transform from scratch, meaning from basic. Okay, from sine waves and cosine waves. Right? So the very first thing I want you to know is to have the concept of basis function. Okay, basis function, that's the basic building block. And sine waves and cosine waves happen to be the basis function that we can use for frequency analysis. Are you all okay? Are you all bored? Should I go further, faster? Go faster, okay. Okay, then we'll do frequency, Fourier transform, something called frequency resolution. Okay, actually some of these terms here, you may not even be able to find it on books or internet, right? I'm using some terms here that will make your understanding easier. Okay? Right? So frequency resolution. And then we will learn something called linear shift invariant system. Those from CEG, you know about this, right? Yes? Linear time invariant systems, you all know about this, right? CG. Right? Linear shift invariance, because you are doing images, so it's shift invariant. Right? And then you have convolution and correlation, and we learned about sampling. I doubt we will have time to go into factorization techniques. I doubt so. Right? We also learn data compression. Right? JPEG, you know, the images JPEG, how do people do JPEG to save the storage space. And we'll go through some application examples also, and including in your and also your project. Okay? Now, you can install MATLAB, by the way, NUS signed license, a very expensive license with MATLAB that allows everyone on NUS account to download everything about MATLAB. Okay, please do so, because MATLAB is extremely expensive. I was from GSO last time, right? Just a very basic license is $5,000 per machine. You buy the 2 boxes, you can add up to 10,000. Okay, it's a very expensive software by NUS. If your NUS account, you can download it, right? And you can work offline, right? So if you can install MATLAB from this link. If it doesn't work, then you can try this link. Okay? Right? So in ancient time, in many civilizations, right? Inca, for example, Inca is one of the oldest. Right? They use various means to record events, right? So this is the earliest form of media, right? And then people progress to using animal skin, paper, and then we have a broadcast station, right? And broadcast, and then you have radio, TV, internet, right? So all these are media. All these are under the topic of media, right? Just to give you a perspective of the kind of things that is relevant, right? And you are familiar with this, right? You're the generation that grew up with Harry Potter, right? Yeah? Right? So if you look at this one, it's not just a simple overlay of a video onto something. Right? Notice that the camera actually zoom into the picture, right? Or zoom in and zoom out, right? When you zoom in and zoom out, the video has to scale accordingly, right? Okay? Now this is the earliest form of something that's related to augmented reality. Okay? So we talk about images, talk about video, right? This is a new form of media, right? That is embedded. The video is embedded into text, right? And presented as such, right? And then when you watch Harry Potter, it's even more impressive, right? So we'll be doing compression, and okay, I think I'll skip this. Right. Now, I am very fond of welcome. Right? This is a full version of the music. You can hear it. Sorry. Components, right? From very low frequency. Low frequency is like high frequency. It's like men speak with lower frequency, women speak with higher frequency, right? So 524 components of them. When you combine them together, you can combine any kind of sound, including this symphony orchestra quality sound, right? So 524 components, right? Now, if I use only the first 5,000 low frequency components, this is what you hear. So you see, you can have a full piece of music, right? You can break them into lower frequency components and higher frequency components, right? In the lower frequency components, you probably hear the, the bass and the very you have not the rhythm has not come in, right? And let's say if I choose 100,000, right? Somewhere in between. This is what you hear. Right? So you begin to hear the music, right? Compared to this full version, you can see that the full version is richer in terms of higher frequency. I'll teach you the skills, right? In taking a piece of music and then break down the different components, and then you can examine how each component sounds like. Okay? Why do you need to do this? Why do you need to do this? You see, when I play for you the 5,000 components, you can hardly make out what song is it, right? You cannot hear that. You don't know what song is this, right? Now, if I go to 100,000, even though it's not as nice, not as clear as 524,000, the 100,000 is good enough for you to identify what music it is, right? Right? So in other words, if let's say, if your boss comes in and say, I have this piece of music, I don't have enough space, right, to store everything, right? Can you store the essentials so that the information is still safe, right? Then you say yes, I can do frequency analysis, and then I just keep the first 100,000 and remove the rest, and this is like how many times? At least 4 times, right? 4 times saving, right? In fact, if you go down to 30,000, useful enough, right? Yeah. Okay. So that is the power. That is the power of learning how to analyze signals using frequency. All right. Okay. So now you see the rationale for doing this course, right? Okay. So I hope you're excited about it and you want to carry on learning more about this. Okay. So and that's the end of this set of slides. Okay. Now usually for the first I'm supposed to give you a 5 minutes break. So we take a 5 minutes break and we come back at 11 o'clock. Right? A plane, right? A two-dimensional plane. Right? When you choose the x-axis and the y-axis, they can be used to represent any point on this plane, yeah? So this plane is a two-dimensional space. Alright? Now similarly, if you are talking about a three-dimensional space, then you have the x-axis and the y-axis and the z-axis, right? And with the x-axis and y-axis and z-axis, it can represent any point in this three-dimensional space, right? Okay? So this is basis function. Okay? I digress a little bit. I tell you a story. We went from two-dimensional, three-dimensional, four-dimensional. We begin to have problem, right? Right? Because our human wisdom or IQ can only take three-dimensional, right? Now, when I was in senior high school, JC here, right? There was a documentary series on cosmos by someone called Dr. Carl Sagan, right? And it's a very good documentary. And he actually made one analogy. Okay? He said if you are living, let's say if our world is two-dimensional, that means we live in a two-dimensional world on this plane. We can only see things on this plane, right? Right? Okay? Now, but actually the space is actually more than two-dimensional, right? Let's say three-dimensional. Now one fine day, if in an alien land here, right? Will you see the entire alien? You don't, right? You see the foot of the alien, right? Right? Okay? And if the alien moves this way, you see that the point is moving, right? It's fine, right? But if the alien jumps, what do you see? You see this point disappear and then it appear again here, right? And when you're living in two-dimensional world, how do you explain it? You say it's spooky, it's ghost, right? Right? And that is because we don't have the wisdom to understand the higher dimensional space, right? Right? So for this course, a lot of times I'm going to use two-dimension on three-dimension to simplify explanation. Okay? But actually, what is happening in the real world out there is higher dimension. Okay? But a lot of times you can understand the higher dimension by looking at lower dimension first, the simplified version, and then you understand here, you can extrapolate to higher dimension. Okay? Alright? So any questions so far? This class, no one has asked any question yet. This class is too quiet. Right? You have to be interactive, then you will learn more. Alright? y, right? Can you have x and y, that is, this x and y is orthogonal, right? Orthogonal means 90 degrees, right? Okay? Can x and y axis be non-orthogonal and still be, let's say 60 degrees, and still be able to represent every point on this plane? Can or not? How many say can? How many say cannot? How many don't know? Okay. The answer is yes, you can. You even if they are not 90 degrees, right? If x and y is this way, you can represent any other point using these two axes also. Okay? Right? But it's actually not convenient. It's not convenient. It's just not convenient, but it's possible. Now, another thing is, I say need not be 90 degrees, right? But if x and y, if x is here, y is also here, right? Can this be the basic function to represent all points on this plane? Cannot. You cannot. Because no matter how you combine x and y vectors, you are only able to represent any point along this line, right? Okay? So in other words, you must have, when you talk about basis functions, you also need to think about the rank, the dimension of the space that you can represent, which is a rank. There's a mathematics term for it called rank, right? Now, if I have two axes like that, x and y axis, I can represent every point on this plane, right? Yeah? If I have these two axes, I can also represent any point on this plane. It's just that it is more troublesome. Right? Why is it troublesome? It's actually in the notes. I'll give you an example. Now, but you cannot represent all points on this plane if the two are aligned. Understand? If the two axes are aligned, you can only represent all points on this line. Right? So, the dimension that the basis functions can represent, right, in mathematical terms is something called rank. Okay? So when the two axes are together, it's rank 1 because a line is dimension 1, right? Right? When you have two lines, two axes that are not aligned, right, is rank 2, right? But this is also rank 2. But orthogonal is easier to, it's more useful. Okay, it's more useful to, and it's more convenient. I would say it's more convenient to represent a point, right? So when we talk about basis functions, the property that we are looking for is actually not just basis, not just the fact that you can represent all signals. We also want the basis functions to be orthogonal to each other. And with this orthogonality, we can derive Fourier transform, okay? Okay, and without this orthogonality, we are in deep trouble. Okay? And it so happens that sine and cosine can be made very orthogonal to each other. So, something useful. Okay? Now, this is, I can skip this, but anyway, this is a very local dessert called ice kacang. Right? You have ice, and then you roll it this way, and then you get a very fine ice here, and then mix with some syrup, and then you eat. Yeah, sorry. Oh, sorry. Thank you. Right. So this is a very local dessert, right? Circular motion, periodic circular motion, and then you turn out some ice for you to eat. Okay, and then you add some syrup here, and it's called ice kacang. If you go to any of the food court here and you ask for ice kacang, they'll give you this. person looking at it, the circle is moving this way, right? If I look at it, what you see is the point going up and down only, right? Yeah? Right? And then if you plot it against the time axis, then you find that it goes up and down, right? Okay? And so from one angle, you see that it is sine. And if you look down, right? If you look from down, the circle moving, if you look down, right? You see that it's also moving left and right, right? So if you plot the time axis this way, it's also left and right this way, right? So from one angle, you see that it is sine. One angle, you see that it's cosine. So that's how sine and cosine came about. Okay? It's not some weird mathematical invention, right? It's actually describing something very physical. Okay? So sine and cosine.
Prof,
yeah.
This one you didn't upload, is it?
No, this one I haven't. This one is for next week. Oh. Because we have time, so I'm talking about this. And next week I'll quickly go through again. Okay? Now in sine and cosine, you write sine and cosine as 2 pi ft, right? Sine 2 pi ft and cosine 2 pi ft. F is the frequency, right? F is the frequency. And frequency, the definition for frequency is number of cycles per second, right? Number of cycles per second. So this is one cycle, right? One cycle, and if this is like 1 second, this will be 1 hertz, right? 1 cycle per second. If this is 2 seconds, then this will be 0.5 hertz, right? Right? Okay, so, and because we are using digital computer to do all our work, we have to discretize the time axis. Okay? Now, to discretize the time axis, you have to represent this t, which is continuous, by this t of n, which is discrete. Okay? Okay? Now, in frequency analysis, there is a profound impact when you switch from continuous to discrete. Right? We'll do that next time. Mathematically, it will give us something very weird. Okay? Now, so, I show you the music comprises 524,000 components, right? Which means that the music comprises 524 frequencies, right? F0 to F 524,000 minus 1. Okay? So this is the frequency component that I was talking about, 524,000 of that. Now, any signal, right? Any signal. This one I have to ask you to believe me first, right? That any signal that you hear, right, can be represented as a summation of sine and cosine. Okay? With different amplitude. Alright? Okay? Now, I have F0 to F 524,000 minus 1, right? So you can use the same set of frequency to represent any signal. The only difference is A and B, you understand? If you use different coefficients A and B, you give you different music, or different speech, different sound, understand? Okay? So when you do frequency analysis, what you're doing is, okay, I'm going to use 524,000 frequencies to represent what I hear. Okay? My task is, for this particular piece of music that you give me, I want to be able to determine AK and BK, I'll know what are the frequency components there. Right? AK and BK, big means frequency is high, right? The strength of that frequency is high. AK and BK 0 means there's no frequency of there's no such frequency in the signal. Understand? Okay? Alright, so the whole idea of frequency analysis is to get AK and BK, and we'll learn how to do that. So K is the total number of frequencies. For example, choosing K greater than 500,000 can represent a piece of symphony orchestra grade type of music well enough, right? The coefficients define the sound that you hear, right? Okay, any sound that you hear can be represented by the same set of frequencies. The only difference is the amplitude of that frequency is the one that defines what you hear. Okay, very important. Now, assuming we are given the values of AK and BK, we vary K from small number to relatively large number, more frequencies being added, and this is what you hear the sound, right? I don't want to repeat now, right? So basis set. The set of as I mentioned, I use 2-dimensional and 3-dimensional, right? But the result is true for other dimensions. No. When you have 2 dimensions, what is the length of the vector that you use to represent the 2-dimensional vector? 2, right? 2 numbers, right? X and Y coordinate. 3-dimension is 3 numbers, right? So the size of the vector n is the dimension of the vector, right? And when you have 2-dimensional space, right? When you have 2-dimensional space, how many basis vectors do you need to represent the 2-dimensional space? 2, right? Right? 3-dimensional space, 3. 1,000 dimensional space, 1,000 of them. Right? And any vector can be represented as a combination, as a linear combination. Linear combination means you sum them up by weighting them. Right? Linear combination, sum them up by weighting them using the factor C to weight the basis vector. Right? So So you can use an orthogonal basis function to represent a 3-dimensional vector, right? And the simplest one to use is 1, 0, 0, 0, 1, 0, and 1, 1, 0, 0, 1, right? X, Y, Z, right? Of course, okay. Let's say if I use 2-dimensional X and Y, right? Orthogonal, right? Like that can also, right, can be a basis function, but they are not orthogonal, right? But let's say if it's orthogonal and I rotate it, can it be a good basis function? Yes or no? It's still good, huh? As long as orthogonal is good. It need not be 0, 1, 0. It need not be this form, 1, 0, 0. It can be a rotated version, it's still a good basis function, understand? As long as they are orthogonal. Orthogonal is more important. You see why later. So why is it desired? Because it's convenient. To get C, we just need to dot product. Look here. Can I assume all of you know what is the dot product of 2 vectors? You're done linear algebra, right? You know what the cross product also, right? Right? We won't use cross product here, we use the word dot product. Dot product means 2 vectors dot product means what? Multiply and sum them, right? I'll be saying a lot of this, the rest of the form, multiply and sum, huh? 2 vectors you multiply point-wise and sum them up, that's the dot product. Okay? Now when you keep, the reason you want the vectors to be orthogonal, the basis vectors to be orthogonal to each other is if you're given any point, right? Right? It's very easy for you to read off the coordinates of the point. they're orthogonal. You just need to do dot product, right? We look at a case, let's see, when it is not orthogonal. They are not orthogonal. These four vectors are not orthogonal to each other, right? E1, E2, E3, E4, not orthogonal to each other. Because when you're orthogonal, when two vectors are orthogonal to each other, when you dot product, what do you get? You get non-zero, right? Yes? When they are orthogonal to each other, when you dot product, you get non-zero, right? Yes? Yes? Yes or not? Oh my goodness. When the two vectors are orthogonal to each other, when you dot product, you get non-zero. Is it correct? Yes? It's wrong, man. When they are orthogonal to each other, the dot product must be zero, understand? Okay? And this is the property I want to use. So when you have E1 and E3, E1 and E2 dot product, what do you get? Zero, right? E1 and E2 dot product with each other is 0.5 times 0 plus 0. Multiply, and sum them all together, you get 0, right? What about E1 and E3? You multiply, plus multiply, do you get 0? So E1 and E3 are not orthogonal, okay? And when they are not orthogonal, if I have a vector 0, 2, 0, 1, 4, and I want to represent this set of basis vectors that are not orthogonal, right? You will get a lot of computations to do. You have a lot of computations to do. Alright? So, but conversely, if you have chosen things like that is orthogonal, right? Right? It's very easy to represent them. Just copy 2, 0, 1, 4, and 10. Yeah? Okay? And we'll see later that you really need this type of orthogonality to do the analysis. So we know that in vector space you have the notion of basis vectors. We also know that in choosing a set of basis vectors, it is most ideal if the basis vectors are orthogonal to each other. Okay? In analyzing signals, we wish to describe the signals in terms of its basis signals. Okay? Now, the challenge is, what should these basis signals be? Right? We do know that ideally this set of basis signals should be orthogonal to each other, and what exactly should be these signals, it depends a lot on what is the purpose of our analysis. Okay? Now, I keep on saying x and y axis, right? And x and y and z axis, right? To represent a point in the space. And that is the location, right? When you want to represent a location in the space, you use x, y, z axis to represent, right? Right? And that is because you are interested in space. Now, when you talk about music, right? You say do, re, mi, right? Do, re, mi. You are talking about your purpose is to represent something in terms of the pitch, right? Do, re, mi, right? Okay? So, using x, y, and z to represent is no longer useful. Understand? Okay? You have to represent the quantity in terms of the do, re, mi. Right? And that do, re, mi is something called frequency. And fortunately, the sine wave and cosine wave give us the notion of frequency, right? Right? If a sine wave, within 1 second, it goes up and down 1 cycle. That is 1/3, right? If within 1 second, it goes up and down for 10 times. That's 10 hertz, right? 20 times. That's 20 hertz, right? So the sine wave and the cosine wave gives us the notion of frequency. So we are going to use another thing is that you find sine wave and cosine waves are very actually close to your. How many of you can whistle? How many can whistle? And this is a very important question. How many of you can whistle? Don't be shy. Can whistle? So few of you. I was thinking of a course project that requires you to be able to whistle. And it's actually easier project. So I ask again, how many of you can whistle? If too few people can whistle, then I cannot do the project. And it's a simple whistle, not you know, in football match and then you want to get attention, you do the long one, not like that. You just whistle the normal way, right? And can I request that if you don't know how to whistle, you start to learn how to whistle? Because if you can whistle, I'll give you a project that requires you to whistle, and it's actually not a difficult project. It's a fun project. So for you, those of you who cannot whistle, can you start to learn? Right? Can you start to learn? As a small kid, when I start to whistle, I whistle by sucking air. But as I grow older, I learn to whistle by blowing the air out. Right? I think it's easier to blow the air out, and try to learn how to whistle. And the reason is this. And I did not realize this until when I did this course and I was designing the experiment. Human whistle is very sinusoidal. If you don't believe, you just use a recorder, a sound recorder, on your app, your phone app or app on your computer. You whistle, you record the sound. Then you look at the waveform. Human whistle is very sinusoidal. You see sine wave. Okay? You see sine wave. And it's single tone. Right? So sine and cosine is actually very close to us. So may I request that those who don't know how to whistle, start to learn how to whistle now. Okay? And if majority still cannot whistle by the time I want to give you the project, then I will give you a difficult one. Okay? It's not that difficult to learn. If you can whistle some simple tune, that's good enough. That's good enough. Okay? Alright. Any questions? Really no questions. Okay, I don't want to keep you too long. 11:30 I can release you now. I think this is the first lesson. I usually don't want to do too much. And then next week onwards, we'll start at 10 o'clock. And yeah. Okay. Thanks for coming to the class and thank you for listening. Right. See you next week. And the tutorial will only start week 3. So next week I'll give you the tutorial timer.